Hi everyone, welcome to this M2D2 talk. Today we have three speakers with us, and they're gonna talk about their work on diffusion model for molecular docking, named DiffDock. So Gabriele, Hannes, and Bowen are all students um, from MIT. Gabriele and Hannes are supervised by Tommy Giacola and Regina Basile. Bowen is supervised by Tommy Giacola and Bonnie Berger. Hannes works on geometry, deep learning, and physics-inspired ML and application in molecular biology and other physical systems. Gabriele research focused on geometry, deep learning, and generative model and the application to challenging problems in biochemistry and physics as well. Bowen works on machine learning for biomolecular modeling and simulation, in particular geometry, deep learning, generative modeling, and physics-informed methods. Thank you, guys, for accepting to present your work to us today. And yeah, without further ado, we can start.
Thank you, Prudential. Well, basically, we work on the same things, just different wordings. But yeah, hi, everyone. Thanks for coming. So today we're going to be presenting DiffDock. So this is joint work with Hannes and Bowen and Tommy and Regina, our advisors. I should say that we are happy to take questions at any times during the talk. In particular, we'll try to give space to clarification questions as soon as they come, and then maybe leave some more discussion-based questions for the end. Okay, but let's get started. So first of all, what is molecular docking? So as many of you probably know, given the topic of the seminar, molecular docking is a fundamental problem in drug discovery, where given a protein and a small molecule, we want to find the structure with which the small molecule binds to the protein. Now, in particular in this presentation, and we can discuss more at the end, we're going to assume that we're given the protein structure, but we won't assume to know anything more about the molecular conformation, so the 3D structure that the molecule is going to take, or the position with respect to the protein that the molecule is going to take. This is often called the pocket. Now, why is this important? Well, most functions in biology are actually mediated by proteins, and small molecules represent most drugs. And so, for example, here you can see the SARS-CoV-2 main protease and the recent Pfizer drug against COVID. And you can see how nicely the molecule binds to the protein. Now, traditional methods for docking are based on what we call the search-based paradigm. And this is formed by a scoring function and a search algorithm. The search algorithm searches over millions of poses, which are then ranked by the scoring function. As you can imagine, this is very computationally expensive and often fails when not given more information beforehand, such as, in our setting, we are considering blind docking where we don't know the pocket. And you can see on the right-hand side, what for now you can think about as success on, so percentage of success on this standard benchmark PDBBind. And you can see that, all these methods are below 25%. Now, the problem with this is that the search space is incredibly large. And so these methods, they're kind of doing not really a blind search, but a kind of traditional search methods kind of fail to find a good pocket, a good pose. So, deep learning methods, especially inspired by the success of AlphaFold, have tried to tackle this task using what we call a regression-based paradigm, and I'm gonna talk about a bit more on this later. And this achieves significant speed up over search-based methods because they can, find the position with one step or a very few steps, but they didn't really show any improvement in accuracy. So you can see on the right-hand side again in red the accuracy of these methods with comparison to the traditional methods. So, we've seen kind of the success that these regression-based models, DiffDock is particularly interesting because it really follows very closely the AlphaFold framework. And so we have seen the success of these methods for all protein folding. Why are they not succeeding for docking? And so, there are a few things that we need to actually understand before to kind of understand this answer. And, the first one is that if we look at this figure on the right, the prediction for docking is only useful if is actually the structure that we predict is very close to the ground truth one. So, for example, the green one is the ground truth, and if we predict the yellow, which is less than Armstrong weight, this is going to be a useful prediction because it can tell us we can probably find more about the affinity. We can tell us which amino acids are interacting and so on. If we predict the red structure, or if we predict something at the other side of the protein, it doesn't really matter. So this is kind of, for this, the standard metric that is used, it's the percentage of predictions that are within 2 Armstrong RMSD, within some small epsilon, which is typically taken to be 2 Armstrong. And in learning theory, this is called, is known as minimum uniform cost, because we're putting a uniform cost on anything that is very close, and then everything that is far away, we consider all of them as a wrong prediction. Now, you could say, we could try to actually use this directly as our objective function when we optimize our neural network. The problem is that this is not differentiable for any epsilon greater than 0. However, we can actually use some insights from learning theory that says if you actually take the limit of this epsilon going to 0, this minimum uniform cost estimator converges to the maximum a posteriori estimator. And so from this, we can actually reason about the fact that the maximum a posteriori estimate is only close to the regression estimate, which is what the regression methods try to find, if our distribution is unimodal. The problem is that with docking, the distribution that we obtain, our posterior distribution of our model, are very much multimodal. And this is for multiple reasons. And in general, the reason is that there is a lot of uncertainty. And this is both aleatoric uncertainty, because maybe there are multiple binding sites in the protein, and epistemic uncertainty, because any method is a very complex task. So it's going to be undecided between multiple poses that might be in completely different points of the protein or with completely different poses of the molecule. And so if we use a regression-based method, this is going to try to find the average of this posterior, the mean of this posterior distribution. And as I'll show you, this turns out to be something very unphysical and very far from the modes that we're interested in recovering. On the other hand, if we use a generative model, this will actually populate all the modes, and we can actually then try to actually find which modes we are most interested in. And so this is kind of the idea behind kind of using generative models for docking. And let me give you a couple of real-world examples. So this is you can see probably that it's a symmetric complex, and this is actually a drug target against malaria. And there is a chromin inhibitor that binds into these possible binding sites. So, since it's symmetric, there are 2 possible binding sites. So if we run a regression model, what we obtain is going to be a prediction that it's right in the middle. Obviously, you don't need to be a biologist to understand that this is actually not a useful prediction. And on the other hand, but that's the best that the model can do, because it's undecided between the 2 binding sites. And so to minimize the mean square error, he has to put something right in the middle. On the other hand, if we run a generative model, we are actually going to be able, and Bowen is going to introduce how we actually build this generative model, but we're going to be able to sample both modes of this distribution. And you can see we can sample them pretty accurately. Let me give you another example where we don't have aleatoric uncertainty, so we don't have multiple binding sites, but still, these methods suffer from all these regression methods, and here our methods suffer from epistemic uncertainty. So the model is a bit undecided between possibly different binding sites. And so you can see that this epistemic uncertainty causes these regression models to actually perform pretty badly. And you can see equibind in light blue on the right-hand side of the molecule is putting half of the molecule in steric clash with the protein. And this is obviously something that is completely not physical, but equibind is still undecided between that binding site and the binding site, or probably on the left-hand side. And so to minimize the expected mean square error, it's going to put the molecule in steric clash with the protein. Similarly, tankbind guesses the wrong binding site, but apart from that, you can see that the conformation that it takes is very distorted. And this is because if you are uncertain about your conformation, you're going to try to put everything closer to the middle, and this is kind of like tankbind's attempts of trying to minimize the expected mean square error. On the other hand, you can see that DiffDock and our generative model is actually going to able to pretty accurately sample the molecule conformation, not have any steric clash or other kind of distortion in the conformer. So finally, once we're going to build this generative model, we're going to be able to sample an arbitrary number of poses, but typically researchers are only interested in one or a very few number of them. So we're going to use a confidence model to rank the predicted poses that come from a generative model, and also give a confident estimate to the user downstream. And this is very useful because for many applications in biology, you probably want to understand how confident the model is about its own predictions. And with this, I'll give the floor to Bowen.
All right. As Gabriel established, we are building a generative model for docking, specifically a diffusion generative model. So how do we do this? Let's go over the basics of diffusion generative models in 3 easy steps. I'm sure this is review for many of you. So first, you look at this, the space that your data lives in this example, a 2D Gaussian, and you define a forward diffusion process in that space that takes the data into some simple distribution like the Gaussian here. In the next step, you learn the score or the gradient of the log density of the evolving data distribution with a score model. And you can think of this as a time evolving vector field. And finally, you use this learned vector field to solve the reverse diffusion, bringing samples from the noisy Gaussian to the data distribution. Now, this example is a toy distribution in 2D space, in Euclidean 2D space. And a ligand pose, you can also think of as being an element of a Euclidean space, right? After all, a ligand pose has n atoms, each of which is assigned to a position R3, so ligand pose lives in R3n. But this forward diffusion, if you were to diffuse it with Brownian motion R3n, hopefully it looks a little ridiculous. And the reason it looks absurd is because too many degrees of freedom of the ligand pose are actually being involved in this diffusion. Instead, in our approach, we take inspiration from traditional docking methods, which instead of trying to reverse the diffusion that completely disassembles the molecule, like you saw on the previous slide, traditional docking methods take as input the 3D structure of a ligand already embedded in 3D space with RDKit. And what this does is it instantiates the bond lengths and angles of the molecule. And then the docking software only modifies the ligand pose through rigid body motion and torsional flexibility to dock it to the protein. This suggests that instead of thinking of a ligand pose as an element in 3-dimensional Euclidean space, we think of it as being described by 4 pieces of information. First are the local structures. So these are the bond lengths, angles, chirality, and ring structures, which are already well determined by RDKit to high accuracy, and we don't actually want to worry about them when we're trying to dock to the protein. And next we have the position and orientation of the ligand, as well as its torsion angles. And these are the ones that we do want to determine with our diffusion generative model. So the punchline is, we want to define a diffusion process that keeps the local structures fixed. And this corresponds to diffusing not over 3-dimensional Euclidean space, but rather over an n+6 dimensional manifold that we call the ligand pose manifold. So how do we diffuse over this manifold? Well, first we map it to a nicer space that we do know how to diffuse over, namely the product space of R3, SO3, and the n-dimensional hypertorus TM. And this is because you can think of a point on the ligand pose manifold, that is a ligand pose, is simply parameterized by these three pieces of information once we've quotiented out, if you will, the other pieces of information, the local structures. So in some sense, we can say that the ligand pose manifold is diffeomorphic to the product space. Now, diffeomorphic is in quotes because there's an additional complication, which is that we don't necessarily need to have a way of mapping ligand poses to the product space itself. Rather, what we need to do is we need to map between displacements on the product space and displacements on the ligand pose manifold. And this is because in score-based generative modeling, you only work with such displacements. Now, maybe this seems like a trivial thing to do, but it's actually not so clear. Because if you ask, if you say you have a ligand pose and you apply some translation, rotation, and torsion, it's actually ambiguous what you actually mean. You need to disentangle these degrees of freedom somehow. And perhaps this need is best illustrated when you consider rotations. If I just ask you to do a rotation, I haven't told you where to rotate around, and so there is some ambiguity. Now, typically one understands that when I say rotation, I mean around the center of mass. And this disentangles the rotational degree of freedom from the translational one by making their infinitesimal actions orthogonal. With torsions, there's actually a similar ambiguity, because if I ask you to apply a torsion, you can rotate one side of the molecule or the other side of the molecule or both. So what do you actually do? So what we do is we define the action of a pure torsion to be one that is orthogonal to rotations and translations. And pragmatically, it turns out that this can be accomplished by rotating the relative, applying relative rotations to whatever side of the molecule you wish, and then doing a post-rotation RMSD alignment. And this turns out to correspond to inducing no linear or angular momentum with the infinitesimal action of torsions. All right, so now that we've mapped displacements onto the product space, we can now just forget about the ligand pose manifold entirely and just figure out how to diffuse on the product space. Turns out diffusion generative modeling is well established on manifolds, as long as you make the slight conceptual modification that instead of the score model being a vector field in the Euclidean space, the score model is a vector field on a manifold. Now, a vector field on a manifold is simply, as the diagram illustrates, a function that assigns to each point on the manifold a point on the tangent space. And furthermore, we need to be able to sample the heat kernel on this manifold and compute its score and sample from the stationary distribution of the manifold. Now, we can do this for each of the elements of the product space, and so we can do so for their direct sum as well, or sorry, for the direct product of the manifolds as well. So here, let's take a look at that in a little bit more detail. So going from left to right, the first element of our product space is the positional degree of freedom. The tangent space there is just the translation vectors. The heat kernel and the stationary distribution are both normal. In the middle, we have SO3, which is the space of orientations. The tangent space, perhaps surprisingly, or maybe not surprisingly, is also R3. And this corresponds to the space of rotation vectors. Now, what is a rotation vector? If you're familiar with the axis angle parameterization of rotations, a rotation vector is very similar, except that instead of the vector being a unit vector, as in the axis angle representation, the length of the vector is itself interpreted to be the angle of rotation. And the heat kernel and stationary distribution here are also known. And finally, on the right-hand side, we have the M torsion angles, and these describe an M-dimensional hypertorus, the tangent space of which is Rm, and the heat kernel and stationary distribution of these are also known. And hence, you can see why our method is called diffusion steps, twists, and turns, because in doing molecular docking, we are implicitly diffusing over the product space of these 3 degrees of freedom. All right, so now that we've examined the forward diffusion, how do we learn the score model? So recall that a score model is something that assigns to every point on the manifold an element of its tangent space. And the tangent space is 3 pieces of information: a translation vector, a rotation vector, and M torsion updates. Now, a point on the ligand pose manifold is simply a ligand itself. So yes, okay, there we go. A score model is something that simply looks at a ligand pose and predicts these 3 pieces of information, which you can very concretely interpret as being instructions for how to update the ligand pose in order to refine it to be a lower noise ligand pose. So how do we build a score model to predict these quantities? Well, we use the by now well-established E3 and N framework, that operates on point clouds. So we have a joint point cloud containing both the protein and the ligand, and we have several message passing layers. And finally, we have readout layers that predict two vector quantities for the global rotation and translation updates, and readout kernels, one for each rotatable bond that predicts the scalar torsion update that should be applied at each rotatable bond. So with this, let's take a step back and go over our workflow. So our first step follows the same paradigms, traditional docking methods. We embed our desired ligand in 3D space with RDKit to instantiate the local structures. Then we sample in random poses, which is from the stationary distribution of our diffusion. So namely normal in the position and uniformly at random in the orientation and torsion angles. Then we simulate the reverse diffusion by taking 20 steps with our score model, which denoises the ligand poses and causes them to coalesce into hopefully the correct binding pocket. And finally, because we can generate an arbitrary number of samples, we would like to have a way of selecting the best ones for downstream processing, which we do with a confidence model that is trained as a classifier specifically for this task. So now that concludes the methods section. And now Hannes will talk about the results.
Yes, but before we do that, we now hope that we know how everything works, right? So now would be another excellent time to ask some questions if we have some unclarities left before we get into results, like maybe how concretely the confidence model works or some other aspects. But if no one speaks up, then we will dive into the results, and we'll be happy that. Yes.
I do have a question on the confidence model. You say you're using a binary classification model to rank the different conformation or other conformation. That sounds a bit strange to me, because like normally you want to rank the poses and select the top 10% or so.
Right, yes. So yeah, the model is trained as a classifier to classify whether a ligand pose is within 2 angstroms RMSD of the ground truth. But of course, you can use the logic of the classifier as a real value score. And in fact, I mean, it does range over all real values. And the poses that the pose that the model is most confident is under 2 angstroms RMSD is the one that we take as the top pose.
Okay.
Basically, it's model confidence that the pose that is predicted is within 2 Armstrong. So it's a binary classification. So you kind of classify whether the model thinks is within 2 Armstrong or not, and you take the confidence of that model as your confidence estimate.
Okay, I see. But by doing that, and coming back to what you were talking about, Gabriele, aren't you forcing then the model to be more or less unimodal in terms of the final set of conformation that is outputted? Like, because everything is within 2 Armstrong of the one conformation instead of different mode of binding that you could explore?
So the way I see it, like your model is going to predict, your score model, generative model is going to try to sample from distribution that it thinks of. Now sometimes these samples, the model, for example, you can see kind of the sample here on the left of the molecule. Probably the initial, at the start, the model thought that it could fit something in that pocket, but then it realizes at the end that that's actually not a good pose. So in this case, it was sort of like discard that prediction. And so potentially you can obviously get obtain, you can have them all returned, all these poses returned. But then if you want to sample just a few poses, then you want to take the ones that the model is most confident about. But for example, in the setting where I showed that there is symmetry or there are multiple binding pockets, then in that case the model is going to be equally confident about good poses on both sides. And so what I'm going to return is actually not a unimodal, it's a multimodal prediction.
Okay, thank you. There's a few questions in the chat, but I think Bowen is taking care of them.
I have a question on the confidence model. I don't know if you're planning on talking a little bit more about this, but I mean, don't get me wrong, the diffusion part is really cool. This whole paper is really great. I think it's fantastic work. But sort of arguably a docking algorithm without a scoring algorithm isn't particularly useful, right? So your scoring algorithm to me is incredibly interesting. And I'd love to hear a little bit more about some of the practicals of how you train that and the architecture and some of those things. I'm not sure if you're planning on going over that.
Yeah, so the architecture is basically the same. The only difference is that the output layer is just prediction. Now I should highlight that this is and Hannes is going to go a bit more over the kind of results that this obtains. But in terms of the way that it's trained, this is really trained to understand whether a pose is good or not. It's not trained to predict like the affinity. So it's not a predictor of affinity. But it's a predictor of, and the way that it's trained practically is we train the score model, then we run our score model on our training data, and we obtain a set of poses for each complex, and then we use our ground truth crystal pose to check whether the predicted pose of the model is within 2 Armstrong or not, and then that basically creates for every pose a classification label. And so then the confidence model is trained to predict this label, this binary label of whether the pose is within or not 2 Armstrong.
Yeah, I think the fact that you use this as a sort of a pose correctness predictor rather than an affinity predictor is actually a huge strength of the method. Traditional docking algorithms try to predict affinity, and that's sort of like a proxy for the pose goodness. And then it ends up being totally meaningless. And I think the idea of whether or not this is actually physical is really powerful. I think that's really cool.
Okay. Then I think Bowen also took care of the questions in the chat. And yeah, we would move on to some results. And the first core set of results here, we will show on the bench, or by now, I guess, standard benchmark PDBBind, where we have 19,000 of these experimentally determined structures of small molecules bound to proteins. And the way the train test split is done is that we have or structures from 2019 or older in our training data, and all of the newer structures we have in our test data. So this is like sort of a time split. And we also make sure that there's no overlap in the ligands. So we never have a ligand in the training set that we also have in the test set. And this is then one test set. And in the other test set, we additionally make sure that we do not have similar proteins in the training set, or we remove all proteins or all complexes from the test set that have a similar protein in the training set. And now we compare our method here then based on this benchmarking setup against methods like Niners Minor, which are these classical search-based methods, but also like commercial tools like Glide, and against these machine learning based or these deep learning based regression methods, EquiBind and TankBind, and E3Bind as well. All right, but then the first core set of results, right? We already saw this here in the beginning, what Gabriele showed us. We have EquiBind here and E3Bind and TankBind, these regression-based deep learning methods, not doing substantially better than the classical search-based methods. And if we now go ahead and combine them, like we combine methods to find the pocket with a classical search-based methods, then this is already a little bit better. But this is not similar to the improvement that we're able to get with DiffDock, where we really put a sizable margin between that and the previous state of the art. All right, so then let's come to another core set of results, which is the runtime, right? Because the runtime really is also crucial if we're looking at docking methods, where we maybe sometimes want to search of tons of molecules and make our predictions there in some virtual screening applications, for example, and we need many 3D structures for downstream applications, and there then the runtime is also important, and we can actually see that DiffDock is 3 times faster than the most accurate baseline. And of course, EquiBind and TankBind are even faster with making their one step prediction or their single shot prediction, right? But of course, this comes at the cost of accuracy and also other nice things that we would like to have, like maybe realistic molecular configurations and physically plausible conformations, because EquiBind and TankBind can actually produce quite a bit of steric clashes and self-intersections in the ligand itself even. And we'll see a bunch of that later as well. All right, but then I also mentioned this test set, right, where we make sure that there's no overlap in the proteins. And we remove similar proteins from our test set. Then the results look like this. And while all methods here, or the performance of all methods here decreases substantially, we, for example, see that Glide's performance doesn't decrease so much. But DiffDock is still better, right? But Glide's performance doesn't decrease so much. But for Glide, we're also not able to make sure that it was not trained on the data that is now present in our test set, right? Because Glide, this commercial tool, is of course continuously updated, and hopefully, and the training data of Glide also, yeah, we cannot make sure that none of it is included in our test set. And when I say training data, right, of course, Glide, maybe we don't associate it with a deep learning based method, or this Sminer Gniner, we do not call it a deep learning based method, but of course there's still machine learning going on, in the sense of these are heuristics functions that are parameterized, and we fit these parameters to data. And if this data is in our is close to the data in our test set, we might have some issues with evaluating generalization. But even under this consideration, DiffDock is still doing better. So we can see that even here we are able to outperform the classical method if we reduce the protein overlap between training and test. Okay, but then let's have a look at some nice visualization of what our inference process actually looks like, right? Bowen explained to you how in the beginning here, we start with all of these random locations, and then for every random location individually, like independent of the other random locations, we ask the diffusion model, how would you want to update the ligand position now? What do you think would be the correct update? And then we apply this update, and then we ask again. And we actually do this 20 times, which is a rather low number of steps, or a low number of reverse diffusion steps compared to some other diffusion models that also work on protein structures or molecule structures that maybe do Euclidean diffusion. And right, this is possible because we reduce the space in which we model the degrees of freedom, or we really only consider diffusion over the relevant degrees of freedom during docking. And here we now see these multiple random starting positions and the animation of how the model updates the positions at each reverse diffusion step. Yeah, and these were these 20 steps. Let's maybe watch again because it's cool. And yeah, maybe I should also mention here in the beginning, this green one, the green thing, that's actually the ground truth. And yeah, in this particular case, DiffDock is able to put the small molecules in very close to the ground truth, right? And then we go ahead and we take all of these positions that our score model, our generative model generated us, and we ask our confidence model which one of these is the best. And that we then maybe use as the final prediction. or we ask it which 5 of them are the best, and then we use those 5 ones as the predictions if we're interested in 5 predictions. Okay, but now if we really only ask for one, and we ask a confidence model which is the prediction in which you are the most confident, then how good is this confidence score actually? So what we see here in this evaluation is the selective accuracy of the confidence score. And what does that mean? Like in this plot here, right? First of all, on the y-axis, we have the percentage of predictions with an RMSD below 2. So the percentage of good predictions, so to say. And on the y-axis, we have the percentage of complexes for which the confidence model is allowed to abstain from making a prediction. So let me explain that a little more. If we're now maybe in an application scenario where we're given 100 complexes, and we know that we need to process 40 of them in some downstream application, and we're able to choose which 40 of them which 40 of the complexes we then in the end want to process further, then we can ask our DiffDock to make all of its predictions, but we then only take the 40 most confident predictions, right? Where we think the error that our model made is very low. And this would then mean when we take the 40 most confident predictions, that we're looking at the percentage of rejected complexes equals 60. So we're now looking at 60 on the x-axis. And now if our confidence model were to just randomly choose the 40 complexes from our 100 complexes, then we would end up with the red line here, right? And if the confidence model were able to perfectly choose the 40 complexes, then the fraction of predictions with an RMSD below 2 would be at the green line here. Like if the confidence model was making its choice based on the ground truth, the distance, the RMSD to the ground truth, like if we had an oracle like this, then we would end up with the green line. And if we now use our actual confidence model, that we trained with this binary classification of whether or not the complex has an RMSD below 2, then we end up with this blue line. And we can see that when allowing our model to abstain from making predictions for 60% of the data, we actually can improve the percentage with RMSD below 2 to around 77%. So in that sense, in the selective accuracy sense, the confidence score is really good. And also, not only it's good in the selective accuracy sense, it is also very helpful to have high selective accuracy, right, for practitioners who maybe are in exactly or a very similar scenario to this. Okay, but then let me finish by showing some predicted structures, some more images. And in this visualization here, for example, on the very left, right, we see the predictions of tank bind. And oh, by the way, these are now 2 different molecules for which we see all of the conformers, and one molecule is in the top row, the other molecule is in the bottom row. And maybe for the top row, the prediction by tank bind, there we see this absolutely does not make any sense. Like this isn't a physically plausible structure, and we have many self-intersections. And we think this happens because we have this regression-based model where we're like if we have uncertainty of where the exact atom location should be, then to minimize the mean squared error, the best thing the model can do is to put everything in the middle with the best thing you can do with a single prediction. And then we end up with these bunched up structures, even if we have some additional constraints that encourage not doing this. Similarly with equibind here, right? In the bottom row, there we also have this self-intersection of the molecule with itself. And with DiffDock when evaluating it numerically, and also like we looked at many examples visually. When looking at them, we never found self-intersections at all, and also much fewer steric clashes than, for example, with EquiBind. Okay, then let's finish up by looking at a set of randomly picked predictions where we're just visualizing here in the top row how the conformers or how the predicted ligand positions look with respect to the protein, and in the bottom row we're zoomed in only on the ligands and looking at the ligands. Yeah, and in green is always the ground truth crystal structure, and in red we have the dark red we have the prediction of DiffDock. And yeah, we see that, for example, in the middle visualization, the prediction of DiffDock, for example, is extremely good. And on the very right, again in dark blue, TankBind produces a rather unrealistic molecule configuration. Okay, but then if you want to see some more examples, feel free to look at all the nice images we have in the paper. But now I'm happy to finish up by telling you that all of our code is on GitHub. We think it's rather easy to use, and we would be happy if more people start using it, which has already been done by others, right? And yeah, with that, we would be very happy to answer any more questions that might be there.
Perfect.
Looks like
Thank
Owen has
you.
been busy.
Yeah, thanks, Warren,
Yeah, Owen has been
so much.
pretty busy. Yeah, thank you guys for the great talk. If you have any question in the audience, please raise your hand and just jump in.
Yeah, and Bowen, if you think there are some questions that are worth discussing, happy to do that.
But one question in the chat is, for example, how important the ESM2 embeddings were for the quality of the predictions. And actually, we ran this ablation. And do you remember the exact numbers?
I think it's about 3-4% improvement. So it's about, I think, 33, I would say, compared to 38. So it's an improvement, but it's even without ESM embeddings, it was much better than previous methods.
Then Jonathan, I think, or Jonathan has a question.
Yeah, thanks again. Really interesting talk. I'll say that this is the first ML-based docking method that the computational chemists in my orbit accepted, or at least are more willing to accept. So it's really cool stuff. One thing I feel like historically these methods use the sort of blind docking as the metrics reporting, which kind of seems, maybe because of the performance of older models, maybe okay, but especially with how good DiffDock is performing, maybe not the most fair comparison. I was wondering if you've looked at docking where the receptor or the domain, and compared to things like self-docking or cross-docking there. And I can give you a little spoiler that I looked at this and it actually still performs really well.
Yeah, so we're actually working on that question, and we are kind of like trying to see what are, because the nice thing about DiffDock is that, since it's a diffusion model, then you can basically change the prior of your, like the prior that you start from, and to focus around a specific thing. It's very easy to add kind of like knowledge that you already have. But exactly the best way of doing this, it's something that we are exploring. Definitely, you can already just filter DiffDock prediction for the ones inside the pocket, but obviously that's not the way that one would want to do it. So yeah, obviously, if you want to focus on the pocket, you probably maybe want to also, like right now, DiffDock actually works at the residue level representation for the score model. Probably one would want to actually operate at the full atomic level, which is something that is also much more computationally feasible within a pocket. But I think there is a lot of work that we're doing to kind of actually make also this more useful also in this known pocket scenario. But one of the motivation for working on the blind docking was, we know that, the search space, becomes so large that this, search space methods kind of like clearly fail. And so this was kind of like a good setting to, highlight the possible contribution. And, now we are kind of like working on the more specific application scenarios.
Yeah, thank you.
Then we have another raised hand, right? Should we maybe go with that?
Hi.
Yes.
Yeah, hi. My name is Thomas Vargo. I'm a synthetic chemist, a medicinal chemist. So I'm not a machine learning researcher. I don't understand a lot of what you've presented, which is fine. There was a comment in the chat, a question about side chains and relaxing the protein and things like that. And so I've actually been using DiffDock for a little while now. I think I downloaded it the day you posted it on GitHub. And I wanted to get a better understanding of how the program interprets side chains, why there is clash, why there might not be, sort of, if you could try to explain it to someone who's not involved in machine learning extremely well, could you sort of help me understand that a little?
Yeah, so actually, the model, so the model that generates the poses, which is what we've been calling the score model, the diffusion model, actually it's working on a residue level representation. So it's only kind of like looking at the backbone and sort of inferring where the side chains are probably be to kind of place the ligand. Now, this is why sometimes we see kind of steric clashes of the side chains with the predictions of the generative model. Many of these are, filtered actually out by the confidence model, but it can still happen. And, intrinsically, that's also due to the fact that we are not right now in this iteration of DiffDock considering side chain flexibility or in general, protein flexibility. Mm-hmm. And so, if you're doing something like cross-docking, we see that, it actually works well. And we can talk about that if we want to. But in general, since we're not considering, flexibility in the protein, there can happen that there is kind of the model has no way of improving the side chain conformations to fit the ligand. So
sorry to interrupt, please continue.
No, go on. I think I'm rambling.
So as a medicinal chemist who's looking at this, we often try to predict binding poses for virtual compounds. So this is the sort of, I guess, cross-docking type procedure, right? And understanding interactions with side chains is pretty critical. And so is there, a relaxation, a method that we could take a DiffDock result if we think it's generally got the pose correct, but it's not sort of, is there some sort of second step that you could imagine being done to refine a pose?
So I think there are two answers. Is there a second step? And the answer is kind of something that we're working on right now, kind of adding some actually modeling the protein conformations to adapt side chain. And also is there a method right now? The answer is I'm not sure. I think for sure you could definitely and some people have done this, which is relax, use some a traditional force field to relax kind of the structure that DiffDock predicts, and they've been we don't have any results on the paper, but we've seen actually people in the industry doing it, and it seems to work relatively well. The other question is, I imagine that you're maybe interested in predicting something like affinity from this prediction. and that's kind of the follow-up question is, do you even need to exactly figure out the sidechain position to predict affinity? And this is also something, how to best predict affinity is also something that we are investigating right now.
Yeah, excellent. Really nice work. Thanks. Appreciate it.
Thank you.
I have one question, guys. So, have you investigated the use of DiffDock for covalent binders?
Oh,
For
sorry?
covalent binders.
Ah, okay. No, we have not looked at that.
Okay.
There might be covalent binders in PDBBind though.
Are you sure that that's possible in PDBind?
Personally, I don't know if there is any
Unless you
covalent
explicitly
binder.
filter for them, they could certainly be in there. Covalent binders are not annotated any differently. There's just an additional connect record, and if the filtering doesn't check for that, then they could certainly make their way in.
Okay.
Okay, I see. Okay, cool.
But I don't know. There may be, there may not be. I don't know.
Okay. Just want to come back also to a comment made earlier by Jonathan, saying that one of the strengths of DiffDock is that the fact that you have a classification confidence model instead of a regular scoring function. And I don't know if Jonathan's still there.
Yeah, I'm here.
Yeah. Again, do you mind maybe elaborating on that? Because from my perspective, I think scoring function are still a huge burden when it comes to docking, and having better scoring function are more needed than trying to get rid of them. Just trying to understand your perspective.
Yeah, so I work in a private drug discovery company, so I'll try to not give away too many reasons as to why I think this might be interesting. But if you just try to do a virtual screen with docking based off of the binding affinity prediction, you're going to have a bad time, right? It's going to be mostly random. But having an independent pose correctness algorithm, to me, adds a lot of strength. Rather than trying to go a little bit further and predict affinity to something that, even as a machine learning person, I wouldn't necessarily trust, but certainly the chemists don't trust at all. So some independent score. I remember when the Aries paper came out, was doing this for like RNA folding, because you can take something like Rosetta fold and then have some independent scoring based off of crystal structures. And that ended up being more powerful than sort of trusting any one algorithm all the way through. So I like it a lot as the sort of independent way to figure out whether or not the pose is correct. And then you can use, more expensive based on, sort of what Thomas was saying, you can run molecular dynamics, you can run scoring, affinity scoring, you can do all this stuff downstream of it if you feel you have a very good, very physical pose, which is a very hard thing to determine, even, computational chemists looking at poses, they don't know, necessarily the right, most physical pose.
Okay. I think understand better. Thank you. One last question for you guys. Have you observed kind of after the first step where you place the different ligand and then did the diffusion, have you observed like clustering of a different binding site for the same protein? Have you observed that a lot? And what have you made of those? Because I guess in those cases, like you have some poses that are very high RMSD and some that are very small RMSD from the non-ligand. So what do you make of those?
Yeah, it's actually quite common. And obviously it happens when you have some like symmetric complexes, because in PDBBind you only have one of the two symmetric poses. So it's actually quite common, but also for non-symmetric, often we see kind of like the poses clustering at different binding sites, especially for large proteins. Now it's actually interesting, often, at least to us kind of like ignorant computer scientists, some of these poses actually look pretty, of the, wrong poses also kind of look pretty, convincing. This seems like a nice pocket and a relatively good conformation in the pocket. Now, we haven't done any analysis to actually figure out whether any of these, pockets or conformations that it predicts are actually valid. Probably most of that won't, but it's actually, I think, something interesting to actually figure out whether some of these extra poses that DiffDock predicts could actually be other, possible binding pockets and binding poses.
Okay, perfect. Thank you. Any more questions? If not, thank you again.
Yeah. Sorry, there were just 2 more questions in chat, and I thought it would be faster to just address them verbally.
Sure.
So the way that we do our filtering is we just directly look at the records in the PDB, and we take the chemical structure of the ligand that is there. So if this is some converted form of the ligand that happened when the binding occurred, then we would be modeling using the post binding connectivity structure of the ligand. So yeah, there could be some weakness / limitation there. So certainly I would trust our method maybe more for non-covalently binding ligands, since now that we know that there's this nuance that maybe we haven't considered.